Afternoon, everybody. Today's speaker of AJS is Simone Vincini, and he'll explain us why is the infinite dimensional sphere point.
Okay. Well, for a start, is everything okay with the audio for people not here?
Yes, everything's okay.
If anybody doesn't hear this then. And I would like to start by thanking the organizer for their work, because I think that these opportunities are really nice for us to share our research with each other and to know better what other people here in SISSA are doing. So I will start by giving you a bit of a disappointment, because the title was mostly a bait, but I'm glad you've taken and you're here despite the snow. But I will spend a minute or two talking about why the infinite dimensional sphere can be regarded as a one-point space. The true topic of the talk is a result about the stability of some quantities with respect to concentration convergence, which is a notion of convergence of metric measure spaces. I know that's a lot of buzzwords, but I will take a bit of a detour before getting there. The first goal of my talk would be to try to give you at least a glimpse of why it is interesting, or at least natural, if you prefer, to talk about nonsmooth structures like metric measure spaces, even if your goal is to look at smooth manifolds and properties of smooth manifolds. And then I'll go on and talk about our results. This talk is based on a work I've done with my advisor, Professor Topology here, and which is in preparation and fully out soon. So obviously it doesn't work. Let's start with a bit of a plan of the talk. I will start by talking about manifolds, inequalities on smooth manifolds, and a rigid, in particular, inequality of smooth manifolds. And I will try to use that as a starting point, using a kind of a variational point of view to make you understand why it is natural to study non-smooth structures. After that, I will talk a little bit about convergence of spaces. And since non-smooth structures, as I said, come up naturally in this situation, I will try to give a little bit of a recap of what happens when our spaces are not smooth and which are the quantities that we're interested in. After that, I will explain which of these quantities are stable in the possible limits, and what was known before our work and what is now known in these situations. So, on the edge of glory, I will be talking about manifolds which are almost extremize some quantity. So, what is curvature? Curvature is kind of a mysterious algebraic object coming out of derivatives of the metric tensor, which encodes some information about the geometry of the underlying manifold. Sometimes some constraint on the curvature yield what are called as rigid inequalities for some quantity of the manifold. Rigid means that whenever these inequalities become equalities, we know on which manifold we're working. So, as some examples, we can look at the Bishop-Gromov inequality, which tells us that whenever the Ricci curvature is non-negative, the volume of balls grow not as fast, or at most as fast as Euclidean balls. And whenever we have equality in the smooth world, we really can say that the balls are Euclidean. Bohnemeyer's theorem tells us that whenever we have some kind of bound on the Ricci curvature, the diameter of our manifold is bounded as well. And again, whenever this inequality is saturated, our manifold is a sphere. We will see that whenever we are in a non-smooth setting, this changes a bit. Finally, another really important kind of property which can extremal property that tells us anything about the geometry of the manifold is the so-called splitting theorem, which tells us that whenever our manifold, which is complete, I will always talk about complete Riemannian manifold, contains a line, maximizing geodesic defined, minimizing geodesic defined on all times, then our manifold is a product. This is not really an inequality, but you can understand that containing a line is kind of an external property, since on every complete Riemannian manifold we have geodesics defined for all times that are minimizing only, usually for small times. You know. Whatever. If we know that these inequalities are rigid, we may try to understand what happens if these inequalities are not really equality, but almost. So if you come, as I do, from a sort of a variational background, there is a natural way to approach this kind of problem. Whenever you have a rigid inequality like this, you can find some kind of topology on the manifolds, such that the sequences that extremize the inequality are compact. Now, if one is able to prove that all quantities in the inequality are stable, I mean, are continuous in that topology, then a simple compactness argument allows us to say that extremizers are almost extremizers are close to real extremizers. Now, what topology should we use in order to study this kind of properties? The story begins with Gromov, probably at the end of the 70s, 78, I think was the first paper, and the realization which started this long journey of discovery was that one should not look only at smooth manifolds, Riemannian manifolds, but should look at a larger class of spaces. This is kind of natural if you think of what happens when you study functional in the calculus of variation. If you want to minimize, for instance, the Ricci energy, you start by looking at smooth functions. Then maybe you put a topology, which is the one-to-one topology, and then you find out that in the limit, non-smooth functions come up, which are the so-called Sobolev functions. In this case, the situation is similar. So the first step was to look at metric spaces, but once one needed to study functional analytic quantities and not just geometric quantities, it resulted natural to look also at what happens at the measure on the spaces, which in the case of Riemannian manifold is volume measure. So how can we compare metric measure spaces, which for what we're concerned with are just complete and separable metric spaces with a probability measure on them? We have two structures to compare. We have a metric and we have a measure. So a sensible thing to do is to fix one of the two structures and compare the other. So a way to produce a topology is to give the so-called Gromov-Hausdorff distance, which boils down to do the following thing. You fix a metric space, you take the two spaces you want to compare, and you embed them into the other space isometrically. You look at what happens to the measures, and you compute some kind of distance of the measures. A natural kind of distance is the so-called Hausdorff distance, which metrizes with convergence. Then once you have done that, you can take the infimum among all possible spaces and all possible isometric dimensions and call that the measured Gromov-Hausdorff distance. And that turns out to be a distance which has important properties. This is not the only way to do the comparison between the structures. Another idea would be just to fix the measure in some way and compare the distances. And it turns out that one could do that as well. Now, you cannot it's not easy to embed spaces into a standard measure space. But what one can do is pick functions from the unit interval with the Lebesgue measure, which is standard in a sense, onto our spaces, and pick functions that preserve the measure. These are called parameters. And once one has two parameters, one to a space and one to another, one can pull back the distances and compute some sort of distance on the pulled back distances. This kind of distance that I wrote here is just some variation on the distance that neutralizes convergence probability. And this turns out to produce, once one takes the infimum among all possible parameters, the same topology as we were discussing before. Now, there are other ways in which one can endow the space of metric measure spaces with this kind of topology. But the question is this meaningful? Can one do anything with this? So there is this amazing result by Gromov, which tells us that if we are interested in complete Riemannian manifolds, which are some kind of bound on the dimension, some kind of bound from below on the Ricci curvature, and a bound on the diameter, then this class is pre-compact with respect to the topology that we were looking at before. Now, the assumption on the Ricci curvature is kind of natural with respect to the inequalities that we were discussing. All of the inequalities had some kind of bound on the curvature. The bound on the diameter is mostly technical. With some modification, one can mostly get rid of it. So the only thing which looks a bit problematic, or may look a bit problematic in terms of what one can or wants to do, is the bound on the dimension. For instance, if one wants to study inequalities that are independent of the dimension, this bound is a bit annoying, a bit, yeah. So what can we do if we want to study sequences of spaces which do not have a bound on the dimension? Well, Gromov gave another kind of answer. It all started from some results of Levy, who proved that, for instance, if one look at spheres, the same spheres which were in the title, so unit spheres with the kind of intrinsic distance, the geodesic distance, and the normalized volume measure. These are metric measure spaces which have a good notion of dimension, which is exploding. But if one only looks at one Lipschitz function, which from a physical point of view can be regarded as some sort of observables on the space, they have a particular behavior. What happens is that whatever sequence of one Lipschitz functions one takes, then as the dimension grows, this function stay on a larger and larger portion of the space, close to a single constant, which may be, for instance, the median of these functions, or one can take the average with a little bit of a worse constant. But I mean, what is happening is that one Lipschitz functions on the spheres are, in a sense, converging in probability to constants. And what are constants? Constants are the one Lipschitz function on the one-point space. So the idea of Gromov was to try to understand this kind of behavior as a convergence of geometric structures of the spheres, as I was saying, to a limit space, which is the point. So let's try to understand how can we make a bit more rigorous this kind of idea. Well, the idea is to build, again, a distance metrizing this kind of convergence. What we can do is argue similarly to what we've done before, fix a single space, which is again the unit interval, and build to measure preserving functions from the interval to our spaces. Once we have these two parameters, we can again pull back the information on the spaces, which is this time the set of observables. Now we have two sets of functions in the space, or measurable functions in the interval, and we have to compare somehow these two kind of sets. And the natural thing to do is to compute a kind of Hausdorff distance with respect to a distance comprising convergence and probability. What we are really doing, we are saying in a sense that whenever we have a sequence of converging spaces, we're asking that for every one Lipschitz function in the limit space, there is a sequence of function on the converging spaces that in some sense converges in probability to the limit function, and vice versa. Whenever we have a sequence of function on the converging spaces which is converging, the limit is yet again a one Lipschitz function in the limit space. Okay. In particular, whenever we have a sequence of spaces converging to the point, the behavior of the function on the spaces is the same as we were observing on the spheres. And this kind of phenomenon can be understood as concentration of measure, which has many other applications in different fields. Now, you can look at this definition. This definition is very natural. It's I'd say, easy to work with if you're trying to prove abstract properties of the distance, but it's not really geometrical, or it's not really clear how to understand compactness, for instance, properties of this definition. One can build the same topology with other techniques. For instance, one can devise a kind of order structure, partial order structure, on the space of metric measure spaces by saying that a space is less or equal to another whenever we have a measure preserving one Lipschitz map, so a contraction, almost contraction in a sense, to from the larger 2B spaces and to the small space. And then once one has this kind of order structure, one can call pyramid associated to a space the set of smaller spaces. And this allows to yet again define the same topology by saying what? By saying that a sequence of spaces converges in concentration whenever the associated pyramids converge in a sort of natural topology to the pyramid associated to the limit space. Now, this construction is probably even more abstract than the one before, but there's a great point, since one can enlarge a little bit the definition of pyramids and show that the space of pyramids is compact. Now, one is saying that we have topological embedding from the space of metric measure spaces into a compact space. The fact is that not all pyramids are associated to metric measure spaces, i.e. the embedding is not on two. This could be useful to associate limit points to every sequence of metric measure spaces, but up to now we don't really know who the limits may be. How can we represent, in a sense, the limits of these sequences? Yet again, as I was saying, even this definition is not really geometrical, not really easy to work with when we're trying to prove really geometrical properties of the spaces. Finally, one has a little bit of a more geometric flavored definition. All this is to say that up to small sets and small errors, one can regard the converging spaces as a sort of fibration on the limit space. There exists a projection that such that the push for all measure do converge, such that the fibers are almost parallel on a good portion of the fibers. And yet again, the property of convergence of Lipschitz function is preserved. And with some attention, one could even localize this property. What we are saying is that almost on all fibers, we have a phenomenon of concentration of measure. So this looks kind of better to understand what is happening at the level of the spaces. Now, before going on, would like to give you some examples in order not just to see the abstract definition, but to have a little bit more of an understanding of what is happening. The first nice important properties is that the distance metrizing or convergence in concentration is less or equal than a distance metrizing the measured Gromov-Hausdorff convergence. So what this is saying is that our topology is weaker. It has to have better compactness properties, which is what we're looking at in order to study spaces with unbounded dimension. Another thing, as I was saying, is that we have an explicit example of converging spaces in the unit spheres of growing dimension. Another nice result is that whenever we have a sequence of smooth manifolds, compact Riemannian manifold with non-negative Ricci, we choose one eigenvalue and that blows up in the limit, then we yet again have a phenomenon of concentration of measure. And it's sad to say, but finally, this is almost everything we have as examples, as explicit examples. This convergence is stable with respect to products of metric spaces. Whenever we have two converging sequences, the products will converge to the product of the limits. And I told you sadly, because as you may see here, we don't really have much more concrete objects to work with respect to the measured Gromov-Hausdorff convergence, which is really well known. So it's a little bit hard to understand if anything goes wrong when one tries to work with this, because the really different objects either converge to one point space, which has almost all properties you want, or are products. So it's quite easy to work with products. So let's start now. I will give a bit of a recap of the quantities we're interested in, because I've talked about metric measure spaces up to now, and if we have nothing to see on metric measure spaces, it's like not really useful to study this kind of convergences. I will be a bit fast, but I just want to give you the basic definition. But if you have any questions, please stop me. Once we are on this kind of nonsmooth spaces, and we want to study, for instance, the Ricci energies in order maybe to study the eigenvalues of the Laplacian, we have to get a replacement for that, because since our spaces are not really Euclidean smooth scales, we do not have derivatives, and we cannot compute the derivatives and integrate them. So we can pick the most smooth functions we have at hand, which are Lipschitz functions, and try to mimic the behavior of smooth functions by computing a replacement for the modulus of the gradient. In the case of Lipschitz function, we can compute the Lipschitz constant on small balls, and then take the limit or the infimum, which is the same thing, as the radius goes to 0. This gives us a quantity which is known as asymptotic Lipschitz constant of the function, and we can integrate the square of that in order to get a sort of a replacement for our Dirichlet energy. Now, this function, as in the smooth case, is not enough to study non-smooth possibly function. So we can relax the definition, and produce what is called as trigger energy, which is the replacement, as I was trying to tell you, of the Dirichlet energy in this case. Once we've done that, once we have a function in the domain of the operator of the function, we can define a sort of replacement for the modulus of the gradient, which is called minimal relaxed upper gradient. We can try to understand the tangent space in a sense of our metric space. And since we want to rule out in some situation the comparison of Finsler geometries, in which case the tangent space is Banach and not Hilbert, we can say that our space is infinitesimally Hilbertian whenever the Chigger energy is quadratic. Finally, if we want to study the Laplacian, which may be interesting for our spaces, we call minus the Laplacian the only element when there is only one element in the subdifferential of our operator. So, in a sense, we are able to mimic a sort of first order differential structures, differential calculus, if we want, on our spaces. Now, another very fundamental notion for the study of these structures is the notion of entropy, the Boltzmann entropy. Whenever we have a absolutely continuous probability measure on our space, we call its Boltzmann entropy the integral of this quantity, the rho log rho, where rho is our measure. Now, the behavior of this quantity can be seen to be much related in the smooth world to the curvature of our spaces. Starting from works from McCann at the end of the 90s, it was understood that in order to understand the topology of the manifold, it can be really useful to understand the topology of the Wasserstein spaces, or some kind of subset of the set of probability measures on the space. So we can put a distance on our probability measure, which is the Wasserstein distance. If you don't know what it is, it's a distance from probability measures, which is really related to the topology on the underlying space. And with this topology, we can say that whenever the entropy has some convexity properties, you see that along geodesics, you see that if k is 0, then this is exactly a convexity inequality. Then our spaces have curvature bounded from below by k. In the case of metric measure spaces, this is a definition, but one can see that in the case of smooth manifolds, this is really a characterization of having curvature bounded from below. In order to study our functional, we can introduce our quantities, which are, like, for example, the slope, which is the speed at which the functional decreases. And it's a kind of a replacement for the modulus of the gradient. A magic fact which happens is that the Chigger energy, our replacement for the Ricci energy, is equal to a constant to the slope of the entropy computed in a measure which has as density the square of our function. Last bit of definitions, and then go on. The last thing I want to talk about is gradient flows. If you are not interested in gradient flows in general, one may think this to be the Chigger energy or the Ricci energy in the smooth world. And a gradient flow for the Chigger energy is exactly the heat flow, which, you know, on manifold is an important object to be understood. So in the smooth setting, we have smooth functional, we have smooth curves, and we understand gradient flows as being curves such that the derivatives is exactly the gradient of the functional computed in the curve with opposite sign. In the non-smooth world, we don't have derivatives of curves, we don't have gradients of the functional, and so we have to do with what we have. If we look at this this equality for a general curve, to this quantity, sorry, for a general curve, we see that we can compute a couple of inequalities, and in general, the minus the derivative of the functional along the curve is bounded by this quantity. What happens is that whenever both of the inequalities are saturated, it all becomes an equality, and the derivative of the gradient flow of the function computed in the curve must be equal up to the sign to the derivative of the curve. So let's go back to the non-smooth world. We say that a curve is a gradient flow for a functional whenever the integrated opposite inequality holds. So we integrate and we replace the differential, the gradient of the function with the slope, the speed at which it is decreasing. Yet again, another magic, which is related to what I was saying before on the Chigger energy and the entropy. Whenever we have a space whose curvature is bounded from below, the gradient flows of the Chigger energy and of the entropy coincide. In which sense do they coincide? Well, whenever we produce a gradient flow of the Chigger energy, we have a curve of functions. If we take the square of these functions and we look at the measures whose density is the square of this function, we get a gradient flow for the entropy. Okay. Now, before starting to speak about what happens in the limit, what is stable, what is not stable, we have to understand what it means for function and quantities on varying spaces to converge to a function or a measure or a generic kind of object on the limit space. Well, the convergence depends its nature on the object and on the kind of convergence we're interested in, but we have a set of definitions which generalize what we're used to work with in the everyday. So, for instance, if we look at measures on a sequence of spaces which can converge either in concentration or with respect to the measured Gromov-Hausdorff topology, we can say that they converge in the weak sense if this happens. Now, what is this? Pn are, in the case of measured Gromov-Hausdorff, can be thought to be isometric immersion in a space where the convergence is taking place. In the case of convergence improbability, these are exactly the projections. So what is happening is that in that case, we are averaging the behavior of measures on the fibers. And then once we have done that, we ask that this average measure converge in the weak sense to the limit. Yet again, in L2, we have L2 or LP is the same. We say that functions converge weakly whenever, after averaging and with a priori estimate, the average function on the fibers converge weakly. And we say that the convergence is strong whenever we have weak convergence and the norms do converge. This, to be more precise, has some kind of consequence on the fibers, because the convergence of norms forces the functions to converge to constants on the fiber. So on one hand, when we are dealing with convergence, we have an averaging phenomenon on the fibers, while once we prove maybe strong convergence, this phenomenon dies. We have constancy in the limit along the fibers. And again, we can define convergence in measure in probability, and the same property of constancy in the limit on the fibers holds for convergence in probability. Now, after all these definition, we can finally have some real results. In the Gromov-Hausdorff case, measured Gromov-Hausdorff case, which has been studied a lot since the seminar results by Villani and Storm. And after that, there's an important paper by G.D. Mondino and Savare. Almost everything is known to be stable. The curvature dimension condition is stable. The entropy gamma converges. If you don't know what gamma convergence is kind of natural convergence for functional, which preserves minimality properties. Under a uniform bound on the curvature, the trigger energy mostly converges, i.e. gamma converges both in the strong and weak topology in L2, which is really important in order to produce a convergence of the heat flows. And yet again, even the slope of the entropy function will converge. With this result at end, one can prove that with some uniform inequality on the spaces, the eigenvalues of the Laplacian do converge in the limit, thereby recovering some kind of stability of interesting quantities in the limit. One can prove that the heat flows is stable. And finally, one can define a meaningful notion of convergence, Sobolev convergence of functions, and then convergence of first order structures on the tangent space. This is what is known in the measured Gromov-Hausdorff case. Concentration in convergence is really much less studied. So many of these results weren't unknown before our work. What was really known was that the curvature dimension condition is stable, the entropy gamma converges, and finally that with a uniform bound on the curvature, the trigger energy gamma converges, but only with respect to the strong topology. This is now not enough to produce convergence of the flows, to talk about the eigenvalues of the Laplacian, to look at what happens to first order structures on the tangent space, and so we decided to tackle this problem. Luckily, not all these properties are more or less true also in our setting. I will now show a bit of these results and how they can be proved. Let's start by the proof, which is really key and instrumental of the convergence of the gamma limit inequality for the slope of the entropy. Let's look at what happens in the Gromov-Hausdorff case. We pick a generic sequence which is converging weakly to a limit measure. We look at what happens to their slope of the entropies, and we would like to prove that the limit inequality, the lower semi-continuity, if you want, inequality holds. The proof is quite simple. The bound on the curvature is instrumental because giving us a bit of convexity, a second order bound, if you want, allows us to see the incremental ratios of the entropy as not only maximum limits, but really supremum of sorry, I said the converse. To see this slope as not only the lim sup of the incremental ratio, but as the supremum of the incremental ratios. Now, one can realize the convergence of our spaces inside a single metric space with a bit of tinkering. One can modify the converging sequence to converge strongly, to converge in the W2 topology, and one can choose a recovery sequence for the entropy converging yet again with respect to the distance we're considering, and then it's easy to see that the incremental ratios do converge. Once the incremental ratios do converge, it's easy to see that their supremum is lower semi-continuous, if we may say so. So all this allows us to prove the gamma limit of this slope, and this in turn allows us to prove with some work all the other results. What goes wrong? In our case, if we look at weak convergence of the measures, the oscillation of the measures along the fiber doesn't allow us to bring back the information about the Wasserstein distance of the limits. So if we look at the two measures, mu1 and mu2, we pick two converging sequences to mu1 and mu2, we have no, in general, that their distance converges, even up to truncation or anything like that. How can we overcome that? The idea, which was like the key result of the paper, was that we can, in a sense, fix one of the sequences and modify a bit the other in order to make its behavior along the fiber follow the behavior of the first, thereby granting us that the distance along the converging spaces converges to the distance in the limit space. And that we can do without throwing away the information on possibly the L-infinity norms, and without paying much in terms of the total variation of the modification that we do. Now, how can we once we've proven that, the same kind of ideas apply. We pick our first sequence, we pick a recovery sequence for the entropy, we modify this recovery sequence. This modification doesn't change much the entropy, but now the distances do converge, and yet the same argument allows us to conclude. How can we do that? Well, the idea of the proof is not really hard. Technical work which was behind is a bit more dense, but the idea is to start from simple cases. If our limit measures are just uniform measures on small sets and the space is bounded, we can just compute another Wasserstein distance of these measures. For this Wasserstein distance, we have a duality formulation, and the function on duality on which we are computing the measures are exactly the one Lipschitz functions, which were our observables. And using this kind of result and localizing a bit the convergence that we had, we can prove that in this case, the result is true. Now, if the space is unbounded, we can tinker a bit, truncate the distance, modify optimal plans, and again, in the hypothesis of having uniform function on small sets, the result is true. And finally, for generic measure, we can cut and paste and approximate measures with linear combination of a uniform function on small sets. And that's all it took to prove the approximation results. Now, once we have this, we can conclude the gamma limit of the slope. And the gamma limit of the slope allows us to pass to the limit in the EDE equality, which was the definition of the gradient flow we are working with. Once we are able to pass to the limit in the gradient flow of the entropy, it is much easier to get the whole gamma convergence, because we just have to prove an approximation result for the slope of the entropy, and the heat flows is a good regularizing object for our measures. Now, given this, we can go on with our program and try to prove the convergence of the Cheeger energy. What was known was that the Cheeger energy gamma converged with respect to the strong L2 topology, and this had something to do with the strong L2 topology killing oscillation on the fibers. The idea here that we had to overcome this problem was to prove a sort of uniform Rayleigh embedding theorem along the converging sequences. So taking a sequence of function bounded in L2 with bounded energy of the gradients, if you want, and a little bit more integrable, we were able to prove by exploiting yet again the approximation result that this function do really converge strongly in L2, and we have a semi-continuity result for the Cheeger energy. Now again, with a bit of truncation and exploiting the fact that the Cheeger energy is more or less the same thing as the slope of the entropy, we were able to prove that we have a full Moscow convergence of the Cheeger energy. And from here on, the path was clear, and we were able to prove the convergence of the heat flows, the convergence of the eigenvalues of the Laplacian, and all that came with that, so convergence of first-order structures, and finally, the convergence of flows of vector fields. Now, before saying thank you to everybody of you for staying here up to the final slide, I would like to tell you one last thing. Why I am not like 5 slides with amazing results and all of that. The problem is that even if we know that this convergence has better properties than the measured Gromov-Hausdorff convergence, for which we have many, many papers, many slides that we have of amazing results, we do not really have either kind of characterization of limit pyramids, if we want to think about limits of sequences as pyramids, or a kind of compactness criterion that allows us to say that once we have a sequence of metric measure spaces, this is compact in the sense that the limit is yet again a metric measure space. So this is the real important open problem to solve. And this maybe, I don't know, maybe a development of the thing. So thank you for being present despite of this. No. Anybody's questions? Please feel free.
Maybe I start with a question. Exactly about your last observation you did. So it's like, do you think that something can be done in this sense? Because, for instance, I don't know, you showed us some like 3 examples of non-convergence in concentration. Basically, you stated like you have a point or products.
Yeah.
This is like everything is pretty much handleable somehow.
Yeah, well, one can play a bit with that. One can pick products and modify it in with a small modification in the measured Gromov-Hausdorff distance, which is a little bit cheating. There is another example that I did not put in the slides, which is the fact that if you take the sequence of spheres and you don't take the uniform measure on the spheres, but you put a small delta in some sequence of points with the mass of the delta not vanishing, what happens is that the limit is disconnected. You get a point and another point with distance half of the maximal quarter, sorry, the maximal circumference of the sphere, which in a sense I think is telling us that this convergence is really intrinsically non-local. One cannot really hope to localize this convergence by fixing a point and forcing that point to go anywhere. And another thing that one may say about this, about pyramids, about what is the limit of pyramid, I think, is that there are some works by Pascoletto which describe another kind of convergence of metric measure spaces, which is called the ultra limit of metric measure spaces, which is really much more intensive from the point of view of set theory and stuff like that, that I'm quite convinced that may be strictly related to this convergence. The main issue which comes up is that in the limit, what he is able to produce are spaces on which distances can become infinite between two fixed points, and the topology fully decouples from the distance. So it is really hard to first to prove that this is really what happens in this case, and second that a characterization like the one we worked with can hold in that situation, because we have projections which are almost one Lipschitz. So if you think that in the limit infinite distances may be produced, sorry, almost isometric, you don't believe that two fibers on measure space with finite distance can have infinite distance between them. I don't know if I was clear in the picture. So it's hard to build a fibration with parallel fibers on a space in which points may have infinite distance between them. So I don't know. This is, I think, a problem in which there is something a little bit deeper to be understood.
I suggest a curiosity. Do you think that the compactness may be searched with a first order condition instead of a second one for this type of variance? Like imposing something at the first order.
What do you mean exactly? Maybe the eigenvalues of the Laplacian?
Can be, but less curvature. Do you think that something less than curvature?
Well, I think so, but for instance, one of the maybe the only criterion I'm aware of at the level of functional analytic properties is exactly a criterion at the level of eigenvalues of the Laplacian, but it only produces sequences which converge to points. And most of the criterion I know of compactness in general produce sequences converging to points. So the thing is that one would like to have, I don't know, some more variety of behaviors, because points are, have all basic properties and none of them. So.
Another one. So, but do you have some criteria to establish if maybe in the limit space you have some dimension bound, something like that?
Not really, but that
Maybe
was
you
exactly what we were escaping from, because this is what happens in the case of Gromov-Hausdorff convergence, in which you bound the converging manifolds and you keep the same bound on the limit.
Yeah.
So if you put the same bound on the dimension on our spaces, you expect to fall in the same kind of phenomena. So
yes, but you don't have the bound on the dimension. So maybe
yeah,
but
I don't know. I find it hard, but because my ignorance to produce a criterion which bounds the dimension of the limit if I don't have bounds on the convergent sequences. But maybe it can be done. I don't really know.
If there are different infinities, it makes sense. But if there is only one infinity, or they are bounded or they're not bounded. If they are bounded, they stay bounded. If they are bounded,
yeah,
yes,
but you may say maybe you have some bound on some other quantities. Which doesn't really tell you that your dimension is bounded, but almost. And you say then the limit must have bounded dimension. Maybe that's
not from the bound, the dimension of the.
No, I was thinking maybe.
Maybe it can be done, but I don't really know, and I wouldn't know where to start to search for that.
Maybe something on this class of Lipschitz function, I don't know, of that manifold if it's smooth.
Yeah, maybe it can be done. I don't really know.
Because saying what is exactly the limit space.
Yeah.
I have a very stupid question. In the inequality, like the almost convex inequality,
almost where in
Same convexity,
K convex, yeah.
The curvature is the Ricci curvature or
Is
the
the Ricci,
sectional?
Ricci.
Usually sectional in these cases.
Sectional you get if you look at geodesics on your space. But these are geodesics of measure. So you're looking at focusing and the focusing effect of measures along. So you can think you have some kind of integral on the directions, and you get trace in a sense. So if you look really at the focusing and the focusing effect on geodesic on the manifold, you get it's not exactly the same, but you get the sectional curvature. But if you look at what happens at the level of measure, and this is one of the reasons because it is interesting to study metric measure manifolds in this setting, you get what happens at the level of Ricci curvature.
Is there any question from home or from the audience here?
Just curiosity, if you have obtained instead like spheres, hypercubes in their surfaces?
Hypercubes is the same. I probably up to some kind of regularity issues, it even comes from this criterion. But maybe in this situation, the most interesting thing to look at is that concentration of measure is a kind of a generalization of the law of large numbers. You have functions which are not means, but are a bit more non-linear maybe. And once in that case, you can, for instance, prove the law of large numbers as a consequence of the concentration of measure in the limit. Because you have these functions of your sequence of random variables, for instance, and they do have to converge to a point, to a constant, which is the limit, a deterministic random variable in the limit.
If there's no other questions, we can thanks for again.